don't need so many pens. So I'll continue with the story that I started to tell yesterday and had already sketched the beginning 10 days ago. And there's some overlap with the lectures that both Martin Müller and I gave at the conference last week. But since I always speak too fast, I always assume it's okay if I repeat things. So let's see if I can figure out my notes. So the theme, well, there were several themes, but one was that you start with functions on partitions. So functions that associate to every partition a number, or maybe something in a more general ring, but if it's a Q algebra, you can always split it up into components, think of just a number. And then sometimes, well, always it gives Q series, so elements of power series in Q. I'll remind you of that. And here there are interesting ones which are modular forms. Well, there are many other interesting ones, but the ones that will be appearing in this context are modular or more generally quasimodular forms. And so sometimes one ends up here. So today I want to talk about the main case of this, which is the Bloch-Okounkov theorem. Last time I gave a special case, which was the theorem discovered by De Graaf and proved by Kaneko and myself. That was a special case. But I also gave a few other examples of functions that don't belong in that setting. And I want to repeat a little bit of that because I kind of ran out of time at the end. I want to give a few more précisions, as one says in French, a few more details, but I won't give the proof of something I considered it, but it's elementary, but would take us too far afield. So I'm going to start. Well, I also need to review quasimodular forms. I said something last time and also very briefly at the lecture in the conference, but I might say some of the things that we care about the most. So let me first have a little section here on modular forms. So this is partly a repeat, but some things I hadn't really said. So if I have a group which is a subgroup of SL2R, I want a group which is discrete and its quotient has finite volume, but in practice I'm only going to talk about SL2Z. In the proof that I gave last time, I also used a slightly smaller group, gamma 0 of 2, but actually for us it'll just be today and from now on it'll just be the full group, the full modular group SL2Z of 2 by 2 integral matrices of determinant 1. And as everyone knows, this acts on the upper half plane, which I write with the German H. If you prefer other fonts, you can use that. The letter for the variable there is always tau, and the action is that the matrix ABCD in gamma sends tau to the Möbius transformation of tau, A tau plus B over C tau plus D. Then I said it last time, that a modular form, so F is a modular form of weight K, which for me will be modular forms of weight K from now on, always on the full group SL2Z, and in fact, only those with integral Fourier expansions. It means, well, the easiest way to say it is that there's a Fourier expansion for all tau in the upper half plane. So the aeons are some coefficients, some complex numbers, but for us they'll be rational numbers, and Q is always e to the 2 pi I tau. This is equivalent, of course, to saying that f of tau plus 1 is equal to f of tau, together with some kind of a growth condition that I won't specify, but it'll be automatic if I have this. And the other condition is that f of minus 1 over tau is tau to the k f of tau. But this is kind of an artificial description, just using the fact that the special group SL2Z or SL2Z is generated by the two maps tau plus 1 or minus 1 over tau, which corresponds to these two matrices, which it's very elementary to show, generate the group SL2Z. So if I had another group, I wouldn't write this, and the general equation everyone has seen, and I'll repeat it. I repeated it last time too. A modular form of weight K transforms under a general transformation, ABCD, with an automorphy factor, C tau plus D to the K. But if the matrix is this, then D is 0, C is 1, and this is just the tau to the k that I have there. Okay, and here, by the way, you see that k has to be an even integer. And in fact, it's automatically non-negative. Otherwise, there aren't any such forms in the case of SL2Z. So that's the definition of a modular form. But then we had things like E2 of tau, which was 1 minus 24 some sigma 1 of n q to the n. Sigma 1 of n is the sum of the divisors of n. And this thing is not quite modular. It's a quasimodular form, which means it satisfies a slightly modified transformation equation, which maybe I'll skip today. But I wrote it. Well, maybe I'll say something in a moment. And so you have this notion of quasimodular forms. Maybe I will say what it is once again, because I want to say something about it. So if I have a quasimodular form of weight k for some group, it means that if I take the same f of a tau plus b over c tau plus b, and I divide by the automorphy factor, this is no longer f of tau, but it's f0 of tau. Well, it's the sum, j from 0 to some p, which is called the depth, which measures how a quasimodular form it is. If p is 0, it's a true modular form. And then there's some function, fj of tau, independent of a, b, c, d. And then it's a polynomial in c over c tau plus d to the j, except in a moment I'm going to want to put, I think, 1 over 2 pi I, maybe minus 1 over 2 pi I. So let me put that. So an example, and then you see in particular that if I take the matrix to be the identity, which is in every group, then f of tau times 1 is simply f0 of tau, so the f0 is f itself. And in particular, you see when p is 0, this is the invariance of the function that says it's a modular form. This is a more general transformation equation. The reason I wrote this again is because you can use the same fj to also define an associated thing. I might get the sign wrong because I didn't prepare it, so there might be a wrong sign. But if you take fj of tau times 1 over, I think it's 2 pi I, but it might be pi I times tau minus tau bar to the j. So this is now a non-holomorphic. These are holomorphic functions. I mean, f is holomorphic. And so everything here is holomorphic. But here, the fj are the same holomorphic functions. Tau minus tau bar is not holomorphic, so this is minus 4 pi times the imaginary part. I might have got a sign wrong. This thing will transform exactly like a modular form. So another way of seeing quasimodular forms, this is how I originally did it in the paper with Kaneko, is that there's an associated object which is modular. Namely, it transforms exactly like a modular form of weight k, but it's no longer holomorphic, but it's nearly holomorphic. That's why quasi-modular. It's a polynomial in 1 over the imaginary part of tau with coefficients which are holomorphic functions, and it's in fact the same holomorphic functions. But the reason I'm writing this is because there's one key element of structure, and I felt it wouldn't be honest to talk about quasi-modular forms and not give some of this structure just as a black box. I mean, one can always just say that the ring of quasi-modular forms is generated by 3 random functions that you write down, as I did, but that's intellectually not very satisfying. That's, of course, not the definition, but the result of some calculation. So I thought I should say a little more, and there's one key point of structure which also involves these fj's, and that's the following. It'll play a role in what we do anyway. There's an action of the group SL, of the Lie algebra SL2 on quasi-modular forms. In this, for any group, it has nothing to do with E2, E4, and D6. So there are 3 elements. One is like, well, if you were a physicist, you would think of the Hamiltonian. W is multiplication by the weight. By the weight. That's an operator, so WF is equal to KF if F is a modular form on any group. It has nothing to do with SL2Z. It doesn't even have to be commensurable. If you have a modular form of weight K, then WF is KF. That's the definition. And of course, if you take 2 modular forms F and G of weight K and L, their product, FG, has weight K plus L, and that exactly means that this is a derivation. So W is a derivation. But I have another derivation. In fact, I have 2 more. So we have 3, which together will commute like SL2. So that means the commutator of W with D will be 2D. The commutator of W with German D will be minus 2 times German D. And the commutator of the 2 Ds will be W, up to sign. So D is actually just d by d tau. But it's very convenient to divide by 2 pi I, which means that as I wrote that last time, if you have a term q to the m in your q expansion, you just multiply it by m, and therefore, if your q expansion had rational coefficients, which I'm assuming, it maintains rational coefficients. So my m star tilde will also be the quasimodular forms on SL2Z tilde, but always, I'll assume without saying it each time, that it's with rational coefficients. So this is, of course, a derivation. It's ordinary differentiation. And D, well, the way the physicists would say it, up to a factor of 12, is that you simply differentiate in E2. But of course, at the level of functions, that makes no sense. You have a function of tau. E2 of tau is another function of tau. They determine each other. I mean, you can invert one power series. What I mean by this is if you know a structure theorem that your quasimodular form, as in the case of SL2Z, happens to be a polynomial in ordinary modular forms and a single other form, which here is E2, then you can think of these as constants for this derivation. So the kernel of this German D, this is meant to be a German D, Fraktur D, is the modular forms. So you think of those as the constants, and then you just differentiate in the other variable. But that's a very poor definition. For instance, there are groups that are not commensurate with SL2Z. There are groups that have, for instance, a compact fundamental domain. Then there's nothing like E2. The structure of M star tilde is not a free algebra over M star. That's only true when there's at least one cusp. But there's still a perfectly good D. I won't explain the definition, but believe me, it exists. So these are the three things. And as I said, they satisfy the obvious inequalities. Not obvious. Two of them are obvious. D increases the weight of a quasimodular form by 2. I mean, the important thing is if you take a modular form, like E4, its derivative is not modular, it's only quasimodular. So it's very important to take this larger ring in order to be able to differentiate. So D preserves quasimodular forms, but it increases the weight from k to k plus 2. That means exactly that the commutator of W, which is the weight operator with D is 2D. Similarly, the other one, German D, decreases the weight by 2, as that means WD is equal to minus 2D. And finally, DD is equal to W, or maybe it's plus or minus or 2. Anyway, it's whatever it is, you check it in any example. So those are the operators, and that's a very important piece of structure. Let me just say it explicitly in the case when gamma is SL2Z, which anyway I'm mostly assuming, then as I already said, M star is Q of E4, E6, which is contained in M star tilde, which is M star, and you adjoin E2. So it's a free algebra on 3 generators, E2, E4, and E6. And in that case, W, since it's a free algebra, every derivative is just a combination of d by dE2, d by dE4, and d by dE6. If you write your function as a polynomial in E2, E4, and E6, and here, since it's just the weight operator, this is a weighted Euler operator. So this exactly multiplies E2 by 2, E4 by 4, and E6 by 6. Then D, that's Ramanujan's formulas, which I'd reminded last time, the derivative, the D derivative of E2 is E2 squared minus E4 over 12. The D derivative of E4 is E2 E4 minus E6 over 3. And the D derivative of E6 is E2 E6 minus E4 squared over 2. And so that's D. And finally, the D operator, as I said, now it really comes into its own. It is 12 D by dE2, because it doesn't see E4 and D6. So in this case, these are the explicit, that's the explicit action of this SL2. And there are many things I won't talk in detail about quasimodular forms. It's not a deep theory at all, but there are many pretty small things. But the key thing about quasimodular forms is that it's an SL2 module in which the primitive elements, the elements killed by the annihilation operator, the one that goes down, which is this, are the modular forms. So one way to see modular forms is as the primitive part of an SL2 algebra. And that's a very nice thing to know. So I'm just saying that, but actually I'll state one or two theorems that use this structure, and so I wanted to have said it anyway. And then finally, to come to this, I said that in connection with this, there's a connection. So we had functions fj, which I defined in 2 different ways, without explaining why it's the same. One is the transformation law of f under a group is a polynomial in C over C tau plus D to the j, but I included a 2 pi to the j for beauty. And then you have coefficients fj. Another way is that the completion you have to complete by making a polynomial in 1 over 4 pi minus 4 pi times the imaginary part of tau. The coefficients fj are again holomorphic functions, but they're the same ones, if I didn't make a mistake. And the third formula, it's that this thing is just like a Taylor expansion. This is just the jth derivative of f, except that it's the jth derivative for this d by de2 operator. So that's another way of seeing it. So you have a kind of a Taylor expansion using this operator. The kernel of Roman D, that's very simple. In fact, I give you an exercise. What is the kernel of Roman D? No? What is D? It's d by d tau. I think everybody in this room, including you, knows the kernel of d by d tau. Yeah, it's C, which is m0 of gamma for any gamma. It's constant. I mean, it's d by d tau. If a function is derivative 0, it's constant. That's not a hard one. And the kernel, by the way, of W, as it happens, since it's multiplication by the weight, is also m0, which is C, but sort of in the opposite order. Here you differentiate the function, find that it's constant, therefore it's modular of weight 0. Here you perceive that the weight is 0, but modular forms of weight 0 are constants. So it's the same answer, but different reasons. Yeah, please. I didn't hear everything, but I think I got the question. It's about breaking up the module. It's completely irrelevant for this course, but it's a good question. It's quite interesting. So let me say very briefly, there are two kinds of groups. I mean, I'm already assuming that my group is discrete and co-finite. So one is H modulo gamma. You should really write it on the left since I'm writing left action. I don't usually bother. H modulo gamma might have cusps, but well, it might be compact. So then if I write the upper half plane as the disk, it's a little easier to draw. Then, well, it should be an even number of sides. Then a fundamental domain for my group might be a sixgon and identify sides. Or it might be non-compact, so non-compact, but since it has finite volumes, it cannot look this. I mean, there are groups like this, but I'm not allowing them because that would have infinite volume. So it might have a fundamental domain that looks like this with a finite number of cusps, which in the upper half plane, well, SL2Z is the most famous example. It goes off to infinity, but for instance, if I took another group, it might look like that with two cusps. So here there exists cusps, finitely many automatically, and they're infinitely sort of go off in parallel if it's finite volume, and here no cusps. And now the structure theorem is that in case 1, m star tilde of gamma, well, of course, it contains C, which is m0 and also m0 tilde. Constants are constant in both senses. But otherwise, it's the direct sum of d to the n times m positive. So if you differentiate a constant, you get 0. It's not very interesting. But if you differentiate a modular form of positive weight, you'll never get 0 because it never becomes constant. The weight goes up, but it becomes quasimodular. And so that's your lowest weight. You see everything being generated by the primitive things. So in that case, everything is uniquely a combination of derivatives of modular forms. On the other hand, in the second case, as SL2Z, that's certainly not the case because we know that E2 is in there, and E2 could not be the d derivative of anything. The only thing in weight 0 is a constant. So in that case, you have to add E2, and also none of its derivatives are there. So what you get there is that there exists a phi. So here, the map D goes, remember, it decreases the weight by 2. But for any group at all, for any group gamma, modular forms of weight 0 are always constants. So D is always a map from M2 of gamma to C. But a map of a vector space to C has only two possibilities. It's 0 or it's surjective. There's nothing in between. So here this map is 0. This map is, is 0. So in that case, that means since, M2 tilde of gamma and M0 tilde. D is only defined on quasi-modular forms. But the kernel of D is modular forms. So in this case, there aren't any true quasi-modular forms yet in weight 2. They only come in higher weight as the derivatives of modular forms. But in the case of SL2Z, we have E2, which is there. And so in a case like SL2Z, when there are cusps, then there exists a phi. So e.g., E2, and actually I'll normalize, so I'll say 1/12 of E2, such that, so now this map is surjective, such that D of, so phi is a modular, quasi-modular form of weight 2. It's not unique, but it exists, such that its derivative, its German derivative, is 1. I've normalized P1. That's why I needed the 1/12. So that's a canonical thing, and in that case, everything is the derivative of either a modular form of positive weight or this phi. So in that case, everything except the constant is uniquely a linear combination of derivatives of that special function phi and of phi. So these are quite different structures. So you could call this, therefore, there's the part coming from all derivatives of phi, and then I'll just call it dm. Well, no, dm, I can include the c. So dm of gamma would be this thing. dm is all derivatives of modular forms. But in this case, every quasi-modular form is a derivative. In this case, it's a bit bigger. What's always true, but I didn't notice it for years, is the dm of gamma itself is closed under multiplication and under the Lie algebra. So this is a submodule and a subring. It's not particularly obvious. You need to prove that. But anyway, it's true. And the last thing is that in this case, there's also multiplicative. Sorry, this is m star tilde. There's also multiplicative theorem. Whether or not it's SL2Z plays no role, but it's always freely generated by this phi as a ring over the ring of modular forms. So it has both a multiplicative and an additive description. In this case here, there's only an additive description, and those are the kind of primitive building blocks. So that is essentially the highest weight decomposition. So that's actually more than I planned to say, but it's kind of nice general culture. And in fact, in mathematics, you'll encounter modular forms, whatever you do, every so often. And some percentage of that time, you'll actually encounter quasi-modular forms. So it's not bad to have seen them, that if you ever need them, you've at least, you know some of the main structural ingredients. But this SL2 action is maybe the most interesting part. So all of that is, as I said, more than I meant to say, but I can't unsay it now. OK, so I think I can erase all of this now. So now I want to go back to the question, how do you get Q-series? Well, that I explained last time. I'll remind you in one line. How do you get a Q-series from an arbitrary function? Any map, so it just associates to every partition some rational number. And then I associate to that f, the Q bracket, which is the average value over all partitions. I won't repeat all the notations. Partition is all partitions of all numbers. If lambda is such a partition, then it's a partition of some integer, which is called the size of lambda and denoted absolute value lambda. There are many, many different notations for partitions, but here I don't care. I'm just, whatever notation, this is what I have, and I divide by the corresponding thing without the f. So this is kind of an average value, so that trivially, in particular, by definition, the constant has Q bracket equal to itself. OK, so this, in general, whether it converges or not, doesn't particularly interest me. This will be a Q series, a formal series with rational coefficients. And then the wonderful discovery, first of de Graaf in this special case, and then of Bloch-Okounkov in a much more general case, and then I found that there are, in fact, many other cases, is that for many, and we don't have any real bird's eye view on which ones, for many kinds of f, so these are, officially this space is called Q to the P maps from P to Q, FQ turns out to be quasimodular. In all the cases, basically that I know it's on the full group SL2Z, but actually I hope I'll be having, if he gets the grant, a student in Holland who's studying various aspects of this, and one thing he wants to look at is whether by putting various conditions you can also produce interesting quasimodular forms with level, something he had asked about. But for the moment, my examples are always in SL2Z. So let me talk about that for a bit. So I ended yesterday's lecture with that, and I'll begin this one, and then I'll go on to the Bloch-Okounkov theorem, which is the main source. So yesterday, so one example we had, one example I already said, the Q bracket of 1 is 1. Another one is the Q bracket of the function Q2 was, so Q2 of a partition was the size of the partition, but then it turned out it would be a very good idea to subtract minus the 24th, and then what you got is minus 24th E2. And more generally, I showed, that was a very simple argument, that if you have any function from partitions to Q, then Q2F is just, and I'll get it wrong, undoubtedly, well, E2, which is, so this is, if it were a ring map, which of course it's not, then you would just from this deduce that that's the answer, but actually the answer is, I think it's minus, it might be, I'll put plus, but it's 50-50, it's whatever I said yesterday, D of FQ. Okay, so those are, so in particular, Q2 as a corollary, if I iterate that, then I get that any polynomial in Q2 is quasimodular, but because I took Q2 of lambda not just be the size, if I'd just taken the size, that's a perfectly good function, but the Q bracket of that would be 1/24th times 1 minus E2, which is also a quasimodular form, but of mixed weight. This is an M0 tilde plus M2 tilde. And anybody who works with modular forms doesn't like mixed weight. A modular form is meant to have a weight. I mean, God intended modular forms to be homogeneous, so although the definition allows mixing weight, you usually try to avoid it. So Q2 is a much better object, but here the weight goes up by 2, here the weight goes up by 2, because that's what D does, and so by induction, this thing is always a quasimodular form of weight 2n, and I gave the first few examples last time. Then another one was Q3 of lambda was this, well, I don't yet have to call it mu3, I can just call it nu t. Nu t I've explained several times, I won't repeat, but mu t, its bracket is 0, or any odd power of it, but if I take an even power, so I take the mth power, I take the qth bracket, it'll be 0 if m is odd, but if m is even, it'll be a quasimodular form weight 3m. So of course, quasimodular forms always have even weight. So, and this is the one that implies Degreff's statement, well, I'll call it his theorem, but maybe not quite proved, the theorem about the generating function of counting degree something covers of a surface of genus M. So in that case, you took M to be 2G minus 2, and this statement was essentially related. This actually has to do with non-connected coverings, and here it's connected. But if you take coverings of a torus by a surface of genus G of some degree D, and you multiply with Q to the D and sum, that generating function is modular, quasimodular of weight 6G minus 6. That was essentially this theorem. So here are various examples. And as I told you, the Bloch-Okounkov theorem says that there are more functions that I haven't yet defined, Qk of lambda. So these are maps, again, from P to Q for all k greater than or equal to 0. And then any polynomial as a Q bracket, which is quasimodular. And in fact, it preserves the grading. If Qk gets grading k, then if you send a weighted homogeneous polynomial of weight k, take the Q bracket, it will be an mk tilde. So that's going to be the theorem, but I have only defined Qk for k equals 0, 1, 2, and 3 so far. So I'll come to that in a moment, but last time at the end I mentioned a few examples which do not belong to this Bloch-Okounkov ring. And actually there's one that I mentioned briefly in the conference last week, and I'll say again today, that by its definition is not in the, I mean, the definition is not from the Bloch-Okounkov ring, but sometimes it turns out to be in it. I mean, it's just a theorem that it is, in fact, a polynomial in these QKs, which I haven't yet defined. So the example that I gave last time, so these are all different examples of modular forms, which that's already 5 examples. So the next example that I gave was SP is a quasimodular form if P is odd. I proved that last time. It was a very simple proof. SP is the pth moment, the pth part moment. So it's the moment of the parts. So if I write the partition, one of the many ways of writing partition is just a decreasing sequence of integers. Then I just take the sum of their pth powers. They're almost all zeros. That's a finite sum. It's an integer. And that function, we found that very easily, in fact, the Q bracket, if I write P as S minus 1, P is positive, of course. Otherwise, you couldn't really take 0 to a negative power. So K is at least 2, and then this thing is simply gk of q, if I permit myself that, minus gk of 0, which I'll also write as gk of tau minus gk of infinity, or I infinity, complete abuse of notations. So gk is really a function of tau, but it's a q series, so it's convenient to write this. So it's the sum, I've defined it twice, I won't repeat, Bernoulli number and the sum of the k minus first powers of the divisor of n, but this thing is a modular form on SL2Z if k is 4, 6, 8, etc., and it's in M2 tilde if k is 2, and it's not modular or quasimodular if k is odd. So SP is not even remotely like QP. They have utterly nothing to do with each other. No, there's absolutely no connection at all. SP is in fact not in this ring at all. No, there's no connection at all, except S2. S2 is Q2 or something. I mean, just for some, or S1 is Q2, because there's nothing else that small. But no, the SP are completely different. So not at all. This is completely different. All of these examples are in the Bloch-Okounkov ring because nu2, I haven't yet defined the QPs, but I have said the QKs, but I did say Q0 is 1 as a function for any partition. Q1 is 0. Q2 I've already said, and Q3 is nu t. So all of these are special cases of this theorem that I haven't yet defined, but SP is not even at all, not even close in the Bloch-Okounkov ring. So let me call this ring. So in other words, if I define the ring R to be polynomials in just letters Q1, Q2, and so on, but then I think of Qk as a function on P, I can embed this into Q to the P, and on that I always get quasimodular forms, but this is not at all in that ring, not even close. It's a completely different object. Then there's another one, which I mentioned last time. Unfortunately, I'm using too many P's. If P of xy is any polynomial, well, since I'm assuming rational, I have to put with rational coefficients, then I make out of a function script A for this polynomial, which is a function from, again, P to the rational numbers. And AP of any partition is the sum over the boxes in the Young diagram. So here's your Young diagram, and then you have a box, and each box has an arm and a length. And the way I normalized, I took the A tilde was the arm length, but including this half a square. So it's a half integer. And B tilde is the length here plus half. So the sum of them together is what's usually called the hook length. And now if you take your arbitrary polynomial of this A tilde of S and minus B tilde of S, then this thing, so this is the definition, and then the theorem, I'll give a mini sketch of the proof. This is also quasimodular. Absolutely true. That doesn't follow from this, but I said it last time. These are not only not in this ring, they're not in any ring that has the good property. So if you multiply already S3, let's say, even though it itself gives a quasimodular bracket, if you multiply it by, Q4 or something and take the Q bracket of that, it won't be quasimodular. So it doesn't even form a ring. These are individual. So it's only a vector space, and these are things in the vector space, whereas that sub-vector space happens to be a ring. It's very puzzling. I was very surprised by that. Once I found that there were new examples, I thought, wow, now we have a lot. We just multiply. But that didn't work. I mean, they just weren't in there. I mean, there was no visible reason that they should, but I assumed it was true, but it isn't true at all. So this example looks a bit disjoint from that. Maybe I'll sketch the proof of this. I was going to do it last time and didn't. So the proof is as follows, but now I want to exactly get my notation so I don't screw up. So I think last time I introduced the notation nm of n. So if m is a natural number, then Rm of lambda was the multiplicity of m as a part in lambda. In other words, I write lambda as 1 many times, R1 times, R1 of lambda, 2 many times, etc. Now I'm not making decreasing, but increasing. So sometimes people write 1 to the R1, 2 to the R2. It's, of course, not correct, but it's very convenient. So that's the multiplicity, and nm of n is the sum over all partitions of n of this Rm of lambda. So it's the number of pairs consisting of a Young diagram and a box, not a box, and a row, a full row, where the row has length n. So if a Young diagram has 6 rows of length 5, it will contribute 5. If it has none, it'll contribute 0. So nm of n is the total number of rows of length exactly m in all partitions of n. And then what I showed, which was essentially a triviality, was that SPQ was, well, what I showed was that some nm of n q to the n was equal to the product 1 over 1 minus q to the j from 1 to infinity times q to the m over 1 minus q to the m. And then with a tiny amount of extra work, that told you that this thing was just the sum over all m to the p times q to the m over 1 minus q to the m, which is equal to what I said if p is k minus 1. That's the Eisenstein series that I didn't define again today. That's up to a constant. That is the definition. So that was the reason this was modular. So for that, I used this nm that I already used last time. But now I want another notation, which is that if a and b are, now let me get it exactly right. Yeah, well, I'll even use my a tilde and b tilde, or I can just call them a and b. They're in f plus, which remember, f I used for the integer shifted by half, and so the positive ones are half, 3/2, and so on. So those are my arguments of this. This is in f plus, that's in f minus, minus f plus. Then I will write n a b of n. It's exactly the same. It's the sum, it's the total number of cells in a Young diagram where the arm length is this a tilde, or a, I called it, and the leg length is b. So that's somewhere, it's one cell in a Young diagram, and those are its arm and leg lengths. So if you have a particular Young diagram, it might have several boxes that have that particular arm and leg length, and it might have none. You count it as many times as you count it, and you add it all up, okay? And so there's a theorem, and in my paper, if you go to my website, you'll find the proof. Since the proof was a complete mess in the literature, it was in 5 different papers, and the statements were not quite compatible, and it was very confusing, so I wrote up a short, less than a page proof, but it's a theorem which is due to Stanley. So the first paper is by Stanley in 1972, Elder, Besser. Don't write all of this down unless you've got a lot of ink in your pen. Bachet, Manivelle. The last author that I had was called Hahn. He rediscovered and then discovered that it was already completely in the literature, but some of these earlier theorems are special case, so this over a period of 25 years, and the proof is also spread over many papers and incompatible notations. But the statement is very easy for all a and b in f plus, and n is anything. NAB of n is simply equal to NA plus b of n. Couldn't be easier. It's very amusing. So a plus b is, of course, the hook length. But here we're not fixing the hook length, we're fixing a and b separately. So I'll give an example from my paper because I don't want to risk making a new one. So as an example, if I take 3/2 for both a and b, and I take n to be 6, then on the NAB side, I have, here's a Young diagram with 6 squares. And here, this one, you see, has leg length 1.5 and 1.5. So the usual arm length would be 1, but I'm adding half. So here's such a square. But of course, you can take the same one, the same box, and you can also take this square. So that's 2 things of length 3/2, 3/2. So I'll draw the whole hook, but the 3/2, 3/2 is here. But you can also take this rectangle, and then there's a unique hook, which is a unique square, which is this one, whose arm and length legs also look like that. And you can also do it for this one. And so therefore, this number is 4. So n 3/2, 3/2 of 6 is 4, because here they are. But for the other, I have to look at all diagrams and count how many rows they have. So here's the 2x3 box. It's a partition of 6. It has that row of length 3. But it also has this row of length 3. But if I take a vertical rectangle, it doesn't have any rows. And the only other one that works, there are 2 others that work. you can take this one as a row of length 3, and finally you can take this one, and that also is a row of length 3, so again, this is also 4. So there's no obvious bijection. I give a proof in the thing. It's not very hard. It's 2/3 of a page long, but it has to do a little bit of work. And as I say, it was proved in various pieces and special cases and general cases in these various many papers. So, and from that, and this implies that with some work. So once you have this, any polynomial is the sum of monomials, and for each monomial, any polynomial, you have to count how many bucks there are with the given a and b, and since you can reduce that to the number n, p of n, then you get this. The only tricky thing is that here, this only is a modular form if p is odd. But because of the minus sign, this sum is symmetric. With each s, I have the dual one, which interchanges a and b, and therefore a minus b would become b minus a, which is, by symmetry, it would be the negative, and so only even polynomials enter, and then for even polynomials, you're left with the ones that work. Okay, so I didn't want to say more about that, but just that we have several non-trivial examples. But then there's a very interesting construction, which I won't repeat. I said it briefly in my lecture at the conference. So this is, I mean, if I count them, well, I won't count them, but I'll circle them, 3, 4, 5. I've already given you 7 examples, plus, of course, the Bloch-Okounkov theorem, which is the main one, which includes many of the others. So another example is as follows. If f in q to the p is arbitrary, then I define the Miller transform of f. It's another function whose value on lambda, and now I can never get the factors right, so I'll just copy them. The value on lambda is 1 over n factorial, so lambda is a partition of some n, and now you take all other partitions of the same number n, but this partition you think of as an irreducible representation. But the other representation you think of as a conjugacy class in Sn. Remember that those things there are bijections between both the conjugacy class of the symmetric group and the irreducible representation of the symmetric group with partitions, and in the handout I gave, well, one of them is trivial, but the non-trivial one was explained there. And so now I think of this as a conjugacy class, then I take the size of the conjugacy class, the value of the character for this representation on any element of that conjugacy class squared, and I multiply by the original f of mu. Okay? Then this implies one line, just use the orthogonality, that the sum, if I take all partitions of a given number n, and I take the Miller transform, mf of lambda, then I get a double sum, lambda and mu, and when I turn it upside down, I get the sum over mu as a partition of n, of f of mu, and then the inner sum is the sum of all of this over lambda, but that sums to 1. And so it's just the same as f mu. So this transform, it's a matrix, p of n by p of n matrix. If you apply it to a vector, you get a new vector, but those two vectors have the same sum. To say differently, if I take this matrix representing this matrix of lambda mu, it's a big p of n by p of n matrix. If I multiply it by the vector 1, 1, 1, 1, 1, I get 1, 1, 1, 1, 1. So the sum of the entries in a vector is not changed, which means, so that's a triviality, and therefore it's a complete triviality, because that's the definition, that f and mf have the same Q bracket. But although that's trivial to prove, it gives us a huge number of new functions, because you take a function you happen to have found, like q2 times q3, or s7, or one of these polynomial things, and you apply m many times to it, it's something completely new, or you apply m inverse. M doesn't have an inverse, it's not injective, but it's a map, so something might be in the image. If you have something which happens to map onto something you've already discovered by m, well, then it has the same Q bracket, so if f was quasimodular, so is mf. So that's a huge source of lots of new examples, and the one that I'm most interested in, well, now I give the last one, Tp is the pth hook length moment. So the hook length of square in the Young diagram is, by definition, the sum of the arm length and the leg length. So usually it's a of s plus b of s plus 1, but I'm taking this tilde where I add a half. So it's just the hook length to the power p. So I sum over all elements in the Young diagram. And I take now not the p, sorry, now I want p minus 1. So it's the p minus first moment, so it's the p minus first hook length moment. And now what's not obvious, it's a theorem that we found first experimentally, or rather we were studying the right-hand side and then found that it was actually equal to the left-hand side. So what actually Martin Müller in his work with OHN, before I became co-author, they were working just on the Siegel-Veech side. They needed to study what then I dubbed in general the Müller transform for this special function Sp, the part length moment, and it did very weird values that we couldn't identify originally, but then with a lot of experimental cases, I guessed a certain formula which turned into this, and then Martin proved it. So this is a theorem. It's not very difficult, but it's a good page using some basic facts about representation of the symmetric group and Young diagrams and so on. It's in the paper. I won't give it. So TP is this, but independent of that, we already knew that TP was not just a modular form, that its Q bracket was not just a modular form, but the same Eisensteins you saw before if P was odd. So this gave another proof because it's the same as for SP. And what we also found later, and that's also in the paper, is that TP, I'll come back to it later, so I'll come back to this example. Well, it's not a new example. TP is, in fact, if P is odd. If P is even, it doesn't have this quasimodularity property. But if P is odd, it not only has that property, it is, in fact, a polynomial in the Q case, but that's not obvious from the definition. It's a quadratic polynomial. I'll write down that formula later. I'm going to say quite a bit more about the TPs. So that's the entire panorama of interesting examples that I know. I know a few other slightly related examples, but it would go too far to give any more. So it's a very interesting fact and completely mysterious that there are so many different kinds of functions that give that. And I've been discussing a bit with various people, in particular with you, if there may be others coming from other places, but it's quite hard to make them. Yeah. They don't form a ring. Oh, you mean since they're in the ring? I don't think so, and it's not a natural question, no. I don't think so. For one thing, they're quadratic, so it would only be an even part. It's not at all a natural thing. There's no earthly reason to multiply TPs that we've found. That's not a good structure. But there's a very good reason to multiply the Qs. OK, so now I'm all ready to state the Bloch-Okounkov theorem. I want to state it and give the proof. And since we're getting on to pause time, maybe I'll give the definition. So I've already defined the Bloch-Okounkov ring. It's the ring generated. Well, it's the abstract ring. R is just the ring generated by indeterminates called capital Q1, capital Q2. But I embed it in this by a Zagier generator to the function lambda goes to Qk of lambda. So Qk has a double role. It's an independent variable that, for instance, I can differentiate with respect to. It wasn't very good English. And it's also a function on partitions. But it's an injective map, so I'm allowed to sort of identify them. So what I have to tell you is what these functions are. I've told you, as I said, but the first few are Q0 of lambda is 1 for every partition lambda. Q1 of lambda is 0. Q2 of lambda is the size of lambda minus the 24th. Q3 of lambda is this nu t of lambda. And I'm going to give you two different definitions, and maybe after the pause I'll say a little more why they're equal. So actually I'm going to give, well, they're actually two different things, and they turn out to be the same up to normalization. You multiply by a certain constant, you add by a certain constant. So if I have lambda, then remember one thing I could do with it was, so what was my standard example that I always used? I want to take the same ones that I have some good numbers to show you. It was 5541. That's the one I used. So if lambda is the partition 5, 5, 4, 1, and since I'm thinking it is an infinite set, I can go on to infinity. So here's 5, here's 5, here's 4, and here's 1. So it's a partition of 15. Then, is that really right? 5, 5, 4, 1. Then you have this maximum diagonal, which I call the H index, but which has maybe the Frobenius index. So R is the length of the maximal diagonal. And then you have the lengths of these things. And I'm always going to work now with the A tilde. So A tilde, the arm length. So once again, I mean, I've drawn this picture. for instance, this area, which would be 3.5, this would be A2 tilde. And similarly, this length, which is 7 halves, 3.5, would be B1 tilde. So A1 is the first, A2, A3, and then it's easy to see that the AIs are strictly decreasing and strictly positive. The BIs are strictly decreasing and strictly positive. It sets of the same length. So I have two R tuples with the same number, and I showed you yesterday how you use that to set up the thing. And well, that's essentially it. And the size of the partition is then the sum of the AIs plus BIs. So if I do that, then I'm going to introduce an invariant, a numerical invariant, which I can write in two different ways. So pk, capital Pk of lambda, is essentially the same as q up to 3 changes, a shift, a multiplicative factor, and an additive factor. So pk of lambda would be the sum, I from 1 to r, of ai, so it's the moment of the k's, but the b's you want to think of as negative numbers, but you want to think of them as being subtracted. It's like positrons and negative, electrons and positrons. So think of this as positive rows. These are negative numbers, but they're also thought of negatively. So you have to take the kth moment of the a's minus the kth moment of the minus b's, which you can write a little more nicely as you associate to lambda a finite set in F. F, remember, was z plus a half. This is going to be a finite set. And now there's no ordering. Here there's an ordering, but I don't really care. Since the numbers are distinct, you can forget the ordering and you can always reconstruct it because you just put them back in order. So if I do want them in order, let's see, B1 is the biggest, so minus B1 tilde, I guess, is the smallest. Minus BR tilde is the next, the biggest negative one. The smallest positive one is AR tilde up to A1 tilde. So if I associate to C lambda the set of A's and B's, but the A's counted positively and the B's counted with a minus sign, that's a positive subset, and this is a balanced subset. And if yesterday I introduced this notation, then please cross it off from your notes. I'll introduce it in a few minutes, but with a slightly different thing. So this is a balanced finite subset. That means that it's a finite subset. So the intersection of F, C lambda with F is finite. Therefore, its intersection with F plus and F minus are both finite, but they're also equal. So this is a set that is equally many things to the left and the right. And again, you want to think of kind of Dirac's sea of electrons. So you think of originally all of the positive positions are empty. Those are particles of spin, let's say a half, 3 halves, 5 halves, waiting to be created. But the negative ones, that's a sea which is completely full. So minus a half, minus 3 halves. But then you can take one here, move it out, and move it to the right, but it could go somewhere else. Then you have as many occupied sites to the right as you have holes to the left. And that's what I'm going to be using in a second. But for now, I'm not doing the whole picture. I'm thinking of this as an actual point, C lambda, not as a hole, and therefore it gets a minus sign because it's really the negative of a point. But in a second, I'll make it an actual point, and then it'll be much nicer. So I'm associating to the partition lambda this finite subset of C, but there's a better thing, and then if I do that, I get this pk of lambda. But the other way that I can do it is I can also associate to lambda the set x lambda, which is the set lambda 1 minus a half, lambda 2 minus 3 halves, and so on. So this is an infinite set, lambda j minus a half. J runs over all positive numbers. And now this set is a subset of F, and it has the property, it starts, these numbers are strictly decreasing. This is bigger than that. So again, I can forget the numbering completely. Since it's a set, it's a set with the biggest element, with the second biggest element. So I can now, to reconstruct the partition, you just have a certain set. And the biggest element, you add a half, and that's lambda 1. The second element, which is strictly small, you add 3 halves, call it lambda 2. So it's smaller than or equal to lambda 1. But eventually, the lambdas are eventually all 0. So this eventually will be minus j minus a half if j is sufficiently large. So how do you see that at the level of the set? Well, it means that x is a subset of these half integers, which I'm calling kind of fermions or fermionic integers. It has the biggest element, so there's only finitely many positive finite number. But in F minus, it's the opposite. After a while, you get every negative half integer, because if j is very large, you get every minus j minus half. So therefore, f minus x lambda is also finite. And not only they're both finite, but they're equal, because that's the picture I drew here. I've taken out as many things on the left as I've put in on the right. And in fact, this set is the same. It just, you have to think about it a couple of minutes. I won't run through it. These two sets are the same as the intersection of the finite set C lambda that I just had with f and f minus. So x lambda, the advantage is you write it directly in terms of the parts. But as a set, it's simply the positive AIs and the negative non-BIs. So it's a set that is not finite to the left, it's cofinite. It contains everything, all but finitely many things. And so then the definition of QK of, now I can finish the definition, and then we make a pause. I think I can erase all of this now. Maybe I'll even skip it and wait till after the pause. So we now have this setup, and well, I can give you the formal definition of QK, but it'll look completely funny, but then I'll give you a natural definition right after the pause. So QK of lambda, if k is positive, Q0 I told you is just 1, QK of lambda is the same as P except for 3 changes I said. First of all, you shift the index by 1, so it's the k minus first moments. Secondly, you divide by beta k, and thirdly, you add a constant. And this constant is simply the coefficient of x to the k in the power series expansion of x over 2 divided by sinh of x over 2. So if you like Bernoulli numbers, well, I don't remember in terms of Bernoulli numbers, beta 0 is 0, the odd betas are 0, beta 0 is 1, beta 2 is minus the 24th, and so on. So these are some rational numbers. So that's why we had that funny. So as an example, P1 of lambda is the sum of the sine. So where did I write it? Pk of lambda. I didn't finish the sentence. The elements of C were A or minus B, so this is simply C to the k, but it's multiplied by sine of C, because these are positive, those are negative. So you see if k is 1, it's the sum sine of C times C is just the absolute value, but the sum, the absolute values of the A's and the B's is simply the size of lambda, and therefore Q2 of lambda, as I told you, is the size of lambda minus the 24th. So this is, at the moment, an artificial definition, but that's the definition of QK. OK, so at least I've now stated the Bloch-Okounkov theorem, because here's the theorem, and here's the definition of the Qs. So let's have a 6-minute break, 6, 7 minutes, till a few minutes past 3. And if there are questions, ask now or after the break. Whew. Oh, sure.
There's some reason that this particular function, so Jacobian of the exponential map appears, so just a coincidence.
Which map?
This it's over half.
Oh, there are yeah, I'm sure this is connected with the Hertzsprung signature theorem and A hat genus and such things, yeah. But I haven't been able to see it. Some of the formalism is very similar, yes. But we can't contain. I mean, of course, in the calculation, there's a clear reason, which you'll see after the pause, but a deep reason, I don't know why it's. I mean, so I have a calculational reason, but not really.
In 2 places, as you say, for the genus and also in
the Todd genus or the A hat genus, yeah. Yes. But where else?
So in conservative deformation quantization, so the so-called Duflo map, and so it's
I'm sure it's connected, but it's
the differential of the exponential map on the real.
I'm sure that's connected, yeah. There is some shift in some differential, but I don't know that point of view, so I can't really answer, but I'm sure the answer is yes. Oh, yeah. No, we'll take turns. He had one, so it's your turn.
When you look at the multiplicativity, actually, you should look at your space modulo the space of function which has 0 brackets.
Well, it doesn't matter. I'm looking at the image. So anything with 0 brackets goes to 0.
Yes, but when we multiply, it doesn't stay true. When you take the product.
It doesn't stay true, but I mean, if I divide by the things with 0 bracket, there's no product at all. It simply doesn't work. It's not an ideal.
I mean, you can always imagine you can add something which
also,
has 0 bracket and such that the product, for example, of the SP, you could modify them.
That means, the problem is it means almost nothing. Almost everybody who sees this the first time, including me when I first worked at it, says, so what's the kernel of this map? What are the things with 0 bracket? It's almost everything. Think what we're actually doing. Think of the 100th coefficient of the Q bracket. So the coefficient of Q to the 100. P of 100 is some large number, let's say 10 to the 23. So an arbitrary function on partitions is simply a 10 to the 23 tuple. and I'm adding all the values. So you say, let's look at all of the vectors that add up to 0. That's practically everybody. It's codimension 1. It's so weak that it means you have no control, but you have no control. No, but then it's meaningless what you're saying, because of course already the Bloch-Okounkov map is way more than surjective. So I can take anything which has a quasimodular Q bracket, and add to it something with the 0 Q bracket so that it's in the Bloch-Okounkov ring, which is a ring. It's way too, well, trivial, but it's completely uninteresting. I have a huge kernel. I mean, this map is not just surjective. We're saying that the map of adding the coordinates of a billion-dimensional space is surjective onto one-dimensional space. That's such a weak, sure, it's surjective. Every map that isn't 0 onto one-dimensional space is surjective. It says almost nothing. When you work with it, you see that the kernel is so big, it's meaningless. I've been thinking now for 6 years about this. I'm convinced there's no cheap way. You either invent a new way to have something which is quasimodular, or you don't. There's no way to cheat and use the, you can't sort of bricoler, construct something. It just doesn't work. Everything reasonable that you look at, I had several theories. All of my tests on the computer, also weaker ones. First, maybe it's not a ring, but it's a modular over the Bloch-Okounkov ring. It's at least, it of course is a modular over Q2, because as I said, Q2 always works, but nothing else. So Q3 doesn't work, nothing works. In fact, of all of these functions, I found only one pair where the product was still had a Q modular bracket, and it seemed to be complete, but quite a big one. So I did a lot of calculations. There was one random one where you could do one multiplication, and it was still quasimodular. And what you said, in a sense, it's true, but it's vacuously true. Since the map already from Bloch-Okounkov, or even from a much smaller thing, is surjective, you can pick something in that small ring that already has the same Q bracket and say, my thing is that thing plus something with 0 Q bracket, but you have no control, so you haven't learned anything. There's no intelligent way, so there's no reasonable section of the Bloch-Okounkov map. And actually, the most interesting part of what I did with Müller, which I'll talk about a little, is about cumulants. Cumulants, the simplest cumulant, is if you have two functions, f and g, and then the cumulant is the failure to be modular. Well, in that case, but in general, if you have many, but you also have an FGH. And already this is extremely hard to study. And it has properties, but it's a very, very subtle set of properties. So there seems to be nothing for free in this game, or even for cheap. I mean, the one theorem we proved was something like 2 years of work even to find the right formulation. And to prove it's very, very hard to construct things that are modular, unless we're overlooking something, but we've tried so many things, I don't really think so. But I was completely amazed when I found that was a paper I wrote alone, and I started playing, and then I suddenly found there are lots of other functions that are quasimodular, but each time for a new reason, and no way to put them together. It looks like, so it's typical when you don't understand what's happening. And being modular is a very strong property. It can't be random. And yet, there seems to be no pattern. I don't see anything in common of these different types of examples at all. And the proofs are all completely different. And the proof that Pixton gave in the conference, he had another example which was quasimodular, and that one did not use it. I asked him, does your map factor through Bloch-Okounkov? Does it lift? Of course, everything lifts because it's surjective, but canonically, and he said they tried. As far as they know, they don't. His thing, it was an inductive process, and each thing was a sum of products of derivatives of Eisenstein series. So it was quasimodular for that reason, but others, the one I'll give, is derivatives with the theta series, because you had a different one, and each time you get a different reason why it works. So even the reason why things are quasimodular is kind of random. Sometimes it comes from Eisenstein series, but sometimes from some other modular forms or special ones. And we don't, it actually doesn't make any sense at the moment, which is one reason it's fun to present. Yeah.
I have another very nice question.
Although it's his turn, but sure, go away. No, I'm just kidding, yeah.
You're always looking at the sum of odd powers of divisors, and when you look at the sum of even powers.
Well, it doesn't work. It's not modular, and there's no properties, no.
Interesting properties.
This has been studied for 100 years. I mean, the odd device as well. I mean, you can do things. There's a larger ring that contains in it some combinatorics, but it has nothing to do with no transformation under a group, no beautiful properties, no finitely generated ring, nothing like that. So, and the same with these TPs and SPs. They're very nice when P is odd, and they're nothing at all when P is even. So that's another thing you have to live with. Actually, in the end, we define TP as twice the natural TP of P is odd and 0 times it. So our TP is always in the ring because it's 0 if P is even. We just put in a factor 1 minus 1 to the P. But it's you can't really, and there's a very good reason for that. Think of the Riemann zeta function, which should be the Euler zeta function. Zeta of 2 up to powers of pi is a rational number. So zeta of 4. Zeta of 3 isn't. Actually, there's nothing except about zeta 3. The theorem is the sum 1 over n to the k, actually 1 over 2 pi I n to the k, for n different from 0, is always a rational number. Simply, if k is odd, it's 0, because the odd ones and the even ones cancel. But if k is even, it's twice the positive. So if you take only the positive, and it's the same with Eisenstein series, it's really a whole sum, and so it's always modular, but half the time it's 0. But if you take the half, then that plus its negative is modular, but so what? It's just not modular at all. It just isn't. That's how it is. Okay, you have a question, but he's used more questions. But now it's his turn. What? Sure, yeah.
I had a question. This is actually about this wide invariant.
Well, no, I don't want to think about anything that's on my course. It's starting 1 minute. If it's not about today's lecture of...
Ich nur fragen, ob
Ja.
du vielleicht morgen Zeit hättest.
Ich habe heute, morgen bin ich in Deutschland. Aber nächste Woche bin ich wieder da.
Sagen wir mal, am Montag können wir da kommen.
Montag, ja.
Vormittag. Hast du da was?
Schick mir vielleicht ein E-Mail. Hast du meine Nummer in Paris? Ich kann dir
Der
das schicken.
Amir hat sie.
Ja, vermutlich. Und auf jeden Fall, du kannst mich auch auf dem Handy erreichen. Mein Handynummer, gerne, ja. Aber ich will jetzt nicht über andere Mathematik denken, was nicht die Vorlesung ist. Das ist eine Frage hierzu. Aber ich will über nichts. Vorsichtig, es gibt eine gefährliche Stufe. Okay, time to start, not time to start. Okay. If there are people outside, call them in. Okay, so I start sort of in the middle of a thought, so this looks very unnatural. I'm going to define these QK. The QK are somehow a little better than the PK, because the PK, although their brackets are quasimodular, they're not of one weight. You have to add this constant if k is even, like we already saw here. Lambda does not work. It gives E2 minus 1 up to a factor, but Q2 is modular. It's truly quasimodular but fixed of a well-defined weight, well-defined homogeneity. But on the other hand, this definition looks completely artificial. So there are two other ways of writing it. One is the one that you'll usually find in the literature, which is exactly the same, actually, as what I wrote, which is, I just had it, and then it disappeared. Well, I guess I can just write it down again, but it's very odd that it should have disappeared on me. Funny, I just looked at it 1 second ago. Maybe it was in my handwritten notes. Anyway, QK of lambda you can also write, well, the 1 over k minus 1 I can't do much about, but if I want it in terms of the parts, rather than in terms of Frobenius coordinates, then I take this lambda j minus a half, and I simply take the k minus first moment of that. But that would be a finite sum for the positive part, but an infinite sum for the negative part. But then, as I said, if I subtract that infinite constant, sorry, minus j plus a half, if I subtract the infinite constant, that's the sum of minus j plus a half k. Now this sum is finite, or it's a terminating sum. Because if j is very large, then lambda j is eventually 0, and then I'm summing 0. So although these numbers are all integers up to denominator 2 to the k minus 1, they're all 0 except finitely many, and therefore this is a rational number. Specifically, it's in 1 over 2 to the k minus 1 times k minus 1 factorial times z. Not that I care, but it's got a specific denominator. So that at least makes this beta k look a little better. And then to make sense of this, you see formally, you can't write it as this sum minus that sum because they're both divergent. But it's easy to regularize. And then you see that what you're doing here is take the sum j minus a half to the power minus s, which is a half to the minus s, plus 3 halves to the minus s, and so on. So this is 2 to the s times 1 plus 1 over 3 to the s plus 1 over 5 to the s, which is 2 to the s times 1 minus 2 to the s, so it's 2 to the s minus 1 times the Riemann zeta function. This makes sense if s, or the real part of s, is bigger than 1, and then this has an analytic continuation, and so you can take s to be a negative number like 1 minus k and make sense of this, and then you do indeed get the same beta k that I defined by a generating function with x over 2 over sinh. So it's just Euler's discovery that the zeta values are Bernoulli numbers. Okay, so that's at least looks a little better. It doesn't really explain why we want these factors and the shift, but at least it explains that there's an infinite constant. But there's another way which is more convenient and which will help us in the proof. So I don't want to raise this definition. So I associated to lambda two different sets. So C lambda was the set of the AIs and the minus BIs. And this set, as I said, is C plus. So I can write this as C plus, which is the intersection. It's the positive part. These are all half integers. So everything is positive or negative. Nothing is zero. So this is the direct disjoint union of its positive and its negative part. And then here, the positive part of this, as I said before, is the same as this, but the negative part is the complement. So this is a set that is in, it's going to be in a set that I may have used that notation yesterday, but if I did, it was a mistake. This is the one I want. I introduce script x sub f, and I'll also have script x sub z with the same definition. And then there'll be a subset of that. I'll put a 0. This is the set of all x in f, and this is the set of all x in z with the same property. So it's bounded above and co-bounded below. So that means here I've my half integers, so I've half, 3 halves, 5 halves, 7 halves, minus half, minus 3 halves, minus 5 halves, minus 7 halves. And my set will have, for instance, 2 positive elements, and it'll be missing 1 negative element and of all others. So that's what I mean by it's, so it has finitely many positive elements, and on the negative side, it has all but finitely many. So, and then xf0 is the subset where the positive part has the same cardinality as the complement of the negative part. Okay, and I do the same for xz, but there's no plus and minus because a subset of z, you can't, not everything is positive or negative. One element is 0. That'll play a big role in a few minutes. So we have this set, and so we now have a bijection. We have a bijection between P and C and X balanced, sorry, also balanced F. So this is finite subsets in F, but balanced, meaning equally many positive and negative elements. And this I just defined. It's balanced in the opposite sense. The positive part is finite, the negative part is cofinite, and its complement has the same cardinality as its positive part. So, and these are these bijections. Lambda corresponds to C lambda, which corresponds to X lambda. So now I want to introduce numerical invariants, not just for partitions, but for any element of xf, or for that matter of xz. And so what I do is the following. I introduce small w. Please, if you're taking notes, distinguish my small w and big, because I'll have both. If x is such a set, so bounded above, co-bounded below, in either f or z, it doesn't really matter, then wx of t is going to be the sum over all of the elements of your set of t to the x. So this will be a doubly infinite power series in t and t inverse times d to the half if x is one of these, well, if it's simply a subset of f. Now I don't need anything because it's just an arbitrary power series. But if x is in this set, sorry, x is a subset of f, arbitrary. But if it belongs to this set script x, which means it's bounded above, co-bounded below, then that means that if t is bigger than 1, it actually converges. And then the negative part, all of the negative things, would be t to the minus a half plus t to the minus 3 halves up to infinity, which is t to the half over t minus 1. So that's if t is bigger than 1. So our series is the sum of all the negative powers plus a finite amount. There's some finite stuff to the right and some finite stuff on the left that you have to subtract from this. So it will actually lie in a smaller space once I first imagine to make it converge, t bigger than 1. Then I think of it as a rational function in square root of t, but it's actually much more. It's t to the half over t minus 1 plus t to the half times now a Laurent polynomial rather than power series. Sorry. So this is wx of t, and then it's very convenient to make a change of variables. That's the large W, capital W, x of z is little w of e to the z. So now you see that in the case that I have when x is bounded above and co-bounded below, and it's a set of half integers, then this will be e to the 1/2 z over e to the z minus 1, but that's exactly 1 over 2 sinh z over 2. Plus, and then it'll be a power series in e to the z over 2. So this thing will have always, independent of what x you take, it's almost a Laurent polynomial in e to the z, sorry, not 1 over c, in e to the z, shifted by half, but then there's a part that's not a Laurent polynomial, it's independent of the choice of x, and it's always 1 over 2 sinh z. And so whatever set I have, my definition now, given any such x, I define w, capital W x of z by definition. Sorry, the definition goes the other way. It has a Laurent expansion at the origin, but it has a pull, and so I shift by 1. So there's an expansion z to the k minus 1, sorry, qx. And so that's the way that I define numbers qk of x for any set x at all of this sort. And then you see that qx of f will be a finite set of pure powers of half integers plus this beta k. And in particular then, if I have a partition, then all notations for partitions are just the corresponding functions for the associated set x lambda. And similarly for the w lambda of t will be w x lambda of t, and capital W lambda of z will be capital W x lambda of z, which will be the sum of the qk of lambda z to the k minus 1. So that's the true definition. So they're the expansion coefficients of this thing. And now you see it's actually very natural. I have done the analytic continuation. I'm just taking this extremely natural definition. You have this infinite set of numbers lambda j. So this, in the case of a partition, w lambda of t would just be the sum, j from 1 to infinity, of t to the power lambda j minus a half, plus a half. Okay, so, and then you expand that. You set t equals e to the z, and expand it. It's a Laurent series. The pull term is always 1 over z, and all the other terms give you the higher qk's. And then if you check, then you'll see that this formula is just what I've been saying. Okay, so now I want to prove the Bloch-Okounkov theorem. But for that, I need one last thing about quasimodular forms that I should have said when I gave my summary. So there's one very interesting function. So I'm going to make a power series in q and in x, but I won't write the q each time. We think of q as sort of wholly unfixed. And so this is the sum. Again, in my lecture at the conference, I gave this, but it was really a summary. Now I'm giving many more details, so I'm sorry I have to repeat. Also, some people weren't there. So I sum over all half integers. This is the classical Jacobi theta series. If you think of q as e to the 2 pi I tau, and if you think of x, z, x as maybe e to the 2 pi I times some other variable u, then this will become the classical Jacobi theta series, one of the 4 classical Jacobi theta series for tau and u. But anyway, I'll just write it. I don't want to take minus 1 to the nu because nu is a half integer, that'd be an I. So I take the integer part of nu, I subtract a half. And then the formula is q to the power nu squared over 8, nu squared over 2, times e to the power nu x. So this is my basic function. So you see that it's an odd function because if I send x to minus x, I send nu to minus nu. That doesn't change nu squared, but it changes the sign of this. So this is an odd function. And so it starts some derivative, theta prime of 0 times x plus dot dot dot. This theta prime of 0 is just the cube of the eta function that we've already seen before. The eta function had the q to the 1/24th, and then it was 1 minus q to the n, and now it's cubed. So that's one of Jacobi's identities, that this sum, the derivative, you just put a nu in front, so this would be the sum minus 1 to the nu q to the nu squared over 2, and then this is some identity due to Jacobi, that thing factors as 8 of tau cubed. But then if you take the whole series and I divide by this theta prime of 0, let me call that the sum hk of q or of tau, I'll just call it hk, times x to the power 2k plus 1. X to the power, let me get the notation exactly the same. It might be No, it's the way I've done it, it's h to the power k plus 1, but the h odd will then be even. It will be 0. E is defined by this. E to cubed is that, so e is q to the 124th, product 1 minus q to the n. It's a famous modular form, and I'm just using that definition because it's familiar to many people, but the statement is this. Anyway, I'll never use it. It's just a notation for now. Okay, so if you divide theta, yeah, then you get an expansion. H0 is 1 by definition, but H2 is E2 over 24. H3 is 0, as I said, the odd ones are all 0. H4 is 5E2 squared minus 2E2 over 5760, and I have H6 here also, but you don't really want to see it. And the claim is that every HK is a quasimodular form of weight K. And this is utterly easy to prove if you know anything about modular forms in many different ways. But the easiest way, actually, is you just differentiate this as it stands many times. Remember, we had the, this satisfies the heat equation. If I apply d to theta, then that will replace q. Remember, d just send q to the n to nq to the n. So if I apply d to theta, that's the same as differentiating twice in x. That's the heat equation. And so using that, you can just start with theta, but I'm differentiating in x, but I can equally differentiate in u. And then you find by practically a one-line argument, you find either a recursive formula or a closed formula. So I can give it as a closed formula. We only want the even h's. It's 1 over 2r plus 1 factorial. It's kind of a Taylor expansion. And then it's this differential operator d plus 1/4, if I didn't make a mistake, e2 to the power r. And you apply that to 1. So you just start with 1. And then every time to go from h to r to h to r plus 1, you just apply this differential operator and rescale. And the proof is 1 or 2 lines. So there's also a 3-term recursion, but this is good enough. So that's the formula for these things, but we don't even care about that. And now is the beautiful thing of this particular proof that I'm going to show you of the Bloch-Okounkov theorem. You don't have to know what a quasimodular form is. You don't have to know what E2, E4, and E6 is. What I'm going to show is that everything will be polynomials in these h's. But since I just showed that the h's are quasimodular forms, they will be. But I'll never use anything modular again. It'll only be the h's. So now comes the theorem, which I stated in my lecture last Tuesday, but I'm going to prove now. So the theorem is this. If F is in the subring Q1 times R, so it's the ideal of R generated by Q1, then I can take theta and I apply to it the operator D. That's not the D we had before, the German D. This D is a derivation on the ring R. Remember, R was the free algebra on all the QKs, so I only have to say what I do on the QKs, and I just reduce the index by 1. So D on any homogeneous element reduces the weight by 1. Therefore, on any element, some power of D eventually kills it. It eventually becomes negative weight, and therefore 0. And therefore, even if I have a power series, this thing is a power series in X, whose coefficients are power series in Q, but there are only finitely many, and so I can apply theta of D to F, and it's got a well-defined element of the ring R tensored with Q of Q. And now if I take its Q bracket, then the formula is now extremely simple, it's 0. And now, before I prove that, let me show why this implies Bloch-Okounkov. So the proof of Bloch-Okounkov, the Bloch-Okounkov theorem, is very simple. There are 3 cases. If F is 1, then we've already seen that the Q bracket of 1 is 1. So that's certainly a modular form and quasimodular. The next is if F is in the ideal, then it's certainly true, because then FQ is simply 0. Because remember, we're taking the average value of f of lambda. F is Q1 times some polynomial, but Q1 of any partition is 0. So then the Q bracket is 0, which is certainly a modular form of whatever weight makes you happy. And finally, if F is in the image under D of this ideal, Well, then what does that mean? Then I can write f as df1, where f1 is in the ideal generated by R. But then, by the theorem, 0 is equal to theta of d, but this is just I can perfectly divide theta of d by theta prime of 0. That's just a function of q. It has nothing to do with the differentiation. And so if you look at this formula, sorry, here it was k plus 1. So here I start with 1, and the first term is 1, is x. But the d here is, x is here, d. So I get d of, sorry, this is f1. It's f1 to which I can apply that theorem. But d of f1 is f. So the first term is fq. Now the next term is e2 over 24. I'll just put h2. It doesn't matter what it is. And then it's h2 times x cubed. But x is d cubed. But d cubed of f1 is d squared of f. And the next term is h to the fourth times d to the fourth fq, etc. And this is now 0. But by induction, since these have smaller weight, these are already quasimodular. And the h's are quasimodular. And so since the sum is 0, this is quasimodular. So by induction, this is also done if you've already proved by induction. And so the remark is simply that R is simply the direct sum of R0, which is Q, plus the ideal generated by Q, plus D. I hope I said it right. Sorry, this is not, excuse me, this is not the ideal generated by Q. I misstated the theorem. Excuse me. It's the exact opposite. Excuse me, I'm sorry. This is the ideal. This is the kernel of d by dq1. So that has a simple name. It's simply the polynomial ring in all the other variables. You don't even notice it when you look at Bloch-Okounkov because q1 is 0 anyway. So if you have a polynomial, you would usually omit the q1. But as an element of the ring, of course, it's completely different. So that's the theorem. If f does not contain q1, and that's what I meant here also. So here f1 has no q1. So it's in the kernel. And the claim is that those three things generate that you just proved by taking a basis. The basis is trivial, it's monomials, and just by put them in lexicographic order, and it's a one-line induction proof. That's very easy to see, that everything can be split into a part that is the image under D of something without any Q1s and something that has a Q1. So just believe me on that part, it's very dull. So this immediately proves the theorem for any element of the ring at all by this simple induction. Excuse me for that stupid. Okay. So now I have to prove this, and the proof of this is actually extremely simple. So let me give that. So the key fact is the following. Well, I could call it a lemma, maybe a proposition, because it's sort of pretty. Remember, we already had a bijection between what I called x f0 and partitions. But now I want to, which way did I write it to make it more beautiful? I put the p to the left. If I take the product of partitions with shifted half integers, remember this is z shifted translated by half, then this is in one-to-one correspondence with xz, which maybe you remember is the set of x and z bounded above and co-bounded below. So the complement is bounded below. So there's the smallest element of z not in the set, and there's the biggest element of z in the set. Okay? And this is very, very simple. If I have lambda and a half integer, then I already had this set x lambda, which was a fermionic set. It was a subset of the shifted integer. So when I just translate it by nu, then it becomes a subset of z. It was balanced. It's now no longer balanced, but I'm not requiring that. It's this. And under this isomorphism, so let's just call this x. And then conversely, given any x, how do I get x? Well, it's as follows. Q1 of x, I'm going to check in a second, is exactly nu. So given any subset of the integers, which is bounded above, co-bounded below, you apply Q1, which remember I defined, it was the first coefficient. So this Wx of z I wrote as the sum qk of x, z to the k minus 1. So that defines the qk for any set. And so Q1, well, I'll check it in a second, it's very, very easy, is nu. So if you give me such a set x, subset of z bounded above, co-bounded below, Q1 is a certain half integer, that tells you nu. Now you take x minus nu, that's now a fermionic set, but it's now balanced. And those were already in correspondence with partitions. So this is a bijection. And I want to tell you what all of the invariants are. So Q2 of x is going to be the following expression. It's the size of the partition under this bijection. X corresponds to the pair minus 2. It's the size of the partition minus a 24th plus mu squared over 2, which already looks good for our theta series. And in general, I'll tell you what qk of x is in a second, but actually I'll tell you even better what f of x is for any function at all. So f is any function in this ring R. You take e to the nu times this derivation. So you know that e to a derivation is an automorphism, nu times the acyclic derivation. So this is an automorphism of the ring. You take this automorphism, so it's a new function on partitions, and you evaluate that on lambda. That's how it goes back and forth. And so in particular, if you do that here, this would be the sum j from 0 to, well, I guess it stops at k. Then here you'd have nu to the j over j factorial. And then it's d to the j of qk, but d just reduces the thing by 1, and then this would be lambda. So this would be the general formula that's an equivalent formula to the first one. So that's the sort of basic bijection, and it's completely trivial to prove. You just have to think of the definition. Remember, to x, we associated little wx of t, which is the sum over all the elements in x of t to the x. Okay? So clearly, if you have any set x and you shift it by any number, in principle any complex number, you just multiply by t to that power, and that's sort of trivial. And remember, we also wrote this as capital Wx of z, where t is e to the z. Okay, so therefore, I know if I just write this out, then you immediately, if I just compare coefficients, maybe I don't even do it. This is equal to e to the nu z, and now this is the sum over k, qk of x. If I do in z coordinates, z to the k minus 1, and this is the same sum with x plus nu, and so you immediately get this formula that when you shift a set by nu, you do that. And then these formulas follow immediately, because the q1 for the partition is 0, so when you shift by nu, you get nu, and the q2 for a partition was lambda minus 1 over 224, and you apply this formula. So all of these formulas are very, very easy. And now I finally give the proof, and the proof now, after all this preparation, is completely empty, practically. Except I shouldn't have removed the definition of theta, so I'll put it back. Theta of x was the sum over half integers of minus 1 to the nu, q to the nu squared. So if I take theta of d, f, q, and I divide, no, I don't divide by theta prime 0, but I do multiply by the sum over all lambda of q to the lambda. So this, by definition, is the sum. When you take the q bracket times this denominator, that's just the sum of this thing over all partitions. So I sum over all partitions, and I have to take now theta of d of f. So in principle, it's theta of d of f of lambda, q to the lambda. But now I use what theta is, and I see that I'm summing over all pairs of partition and a half integer. And now if I put in this definition, I get minus 1 to the nu. And then I've e to the power nu times d, because I'm taking theta of d. So it's e to the nu d of my function, evaluated on the partition, minus 1 to the nu, and then I've q to the nu squared over 2. But then from the original definition, I've q to the power nu squared over 2 plus lambda. And actually, I would prefer here to put minus a 24th, because that's eta inverse, and so here it's minus a 24th. I mean, it doesn't really matter, but I want it. Okay, but now, by the proposition, there's a bijection between pairs, a partition and a half integer, and subsets of the integers, which are finite above and cofinite below. And now, under this bijection, q, where's it gone? Under this bijection, the x corresponding to the pair lambda nu q1 of x is nu. So this first number is minus 1 to the power q1 of x. then e to the nu delta f of x is exactly of lambda, which is what I had, is exactly f of x. Something seems to have gone, maybe it's right. And then this last thing, q2 of x was exactly lambda minus the 24th plus nu squared over 2, which luckily is just what we have, q2 of x. And this thing involves only q2, q3, and so on, but no q1, right? Because f didn't involve q1, and q2 involves q1, so the q1 is only here. And now, this is 0. And the reason is, if I have x, any element of xz, I send it to x star, which means that you take the union of x with 0. If 0 is not already an x, you add it. And if 0 was an x, then you remove it. So that's obviously an involution. You just add 0 modulo 2, as it were. Then what happens to the qk's? Well, the w, x star of t, was the sum of the t to the x, but you've only added 0 or subtracted 0. So it's the original x plus or minus 1, which, since this has a Taylor expansion with qk, it says the qk of x star is equal to qk of x if k is at least 2. But q1 of x star differs from q1 of x by plus or minus 1. So now we're done, because when I apply this involution, I send x to x star, q2, q3, and so don't change. This is unchanged. q1 of x changes by plus or minus 1, so it changes parity, and so the terms simply cancel in pairs, and therefore I get 0. So that's this proof, which if you compare with the proof I gave yesterday for the special case q3 to the k with an induction over derivatives of Eisenstein series on gamma 0 of 2 and so on, it was much more calculational, much less convincing, and it was only a special case. So that's I think, a very cute proof. So now I've spoken so slowly that I still have time left. So I'll stop talking for a minute so you can breathe and look what else I still tell today. I meant to give a numerical example, but it's too late now. From my partition 5541, I was going to write out these various invariants. Are there questions on this? Because this is, in a sense, the heart of the course. I wanted to show how to use the Bloch-Okounkov theorem and this thing of going from functions of partitions, and therefore to do with representation of the symmetric group, to the world of quasimodular forms. And then in the remaining time, so especially next week, I'll describe a little bit the applications to the Siegel-Veech story and volumes of Stradian moduli spaces. But the key thing that makes everything work on the combinatorial level is this story. And this Bloch-Okounkov theorem, I think, is just a real marvel. And I also want to put it in context. That's why I gave these many other examples of functions that don't quite belong to this ring, but still give quasimodularity. So it's a very mysterious story. I think very, very pretty. And even if you couldn't follow every detail, it's written up and there'll be notes, but it's also on my homepage. You can see that this is not a hard proof. It can be presented in 10 minutes. Maybe that's too fast, but there's no higher, it's not rocket science, as they say. There's nothing really difficult going on. The hardest thing was taking 0 out of a set and putting it back in, which is what Eeyore used to do with the balloon, so it shouldn't be very hard for us. Okay, so I'll erase a bit, and then you can think if you have any questions on this. So, I do know what I want to say. So I'll talk next time about this story with TP. Sorry, was there a question? I don't see a hand, but now I see. Yeah.
Can you give me an interpretation?
Within the infinite wedge? No, that's like many of the questions that were asked in the first 2 weeks of the course when people, maybe you too, asked, can you do this topological recursion, Gromov-Witten invariants, infinite wedge, Fock space? I said, that's what Pandry Pand and Okounkov and all these people did 10 years ago. I'm trying to do it kind of very advanced high school level, go the other way. The paper by Bloch and Okounkov uses the infinite wedge. That's how they do it. And it's very, very beautiful. They give 2 proofs, as I think I mentioned. One carefully follows the proof that I gave yesterday, my proof with Kaneko, with the Eisenstein series on gamma 0 of 2. It's very calculational. It's ugly, but in 4 pages they're finished, 6 pages. But it's very ugly. Ours was very ugly, and it becomes a little uglier by being more general. And then they give a wonderful proof that you do get some understanding using the infinite wedge representation. The name of their paper contains infinite wedge representation in the title. But the fact remains that not only you need to know a lot of mathematics, that I've learned some of now but didn't know before, but it's also a 20-page proof. This is a 3-line proof. So I simply have no desire to translate it back, but yes, it does, and it's sort of clear, and I mean, some of the annihilation and creation operators you see in this infinite sea of electrons, you see bits and pieces, but the advantage is here, there's no algebra, there's just nothing. It's very easy. But, I mean, their paper is really a wonderful paper. What I didn't say, they also give kind of explicit formulas for the so-called endpoint functions. So in order to actually compute this, I should say this, there is no closed formula known directly for this Q bracket as an element in M star tilde. I don't just mean it's a polynomial in E2, E46. That's a completely artificial way to write things. It might be anything else. You apply differential operators, products, theta series, Eisensteins, put in anything that you know is quasimodular. I'd allow all of that. I don't mean a polynomial in the 3 generators, but there's still none known. We've only inductive procedures. There is something I'm going to explain next time, something called the evaluation map, which goes from modular forms or quasimodular forms to polynomials. And that was done by Eskin and Okounkov, and we found a simpler way, and also a different theorem. So we have 2 formulas. There is a formula for the image of the Q bracket. If you combine these 2 things, then this is known in kind of a nice generating function. But there's no formula for the original. But on the other hand, to know it, since it's the free ring generated by something, you could either do Q1 to the N1, Q2 to the N2, that's one basis, or you always have a choice, M1 up to QMN, where these are just positive numbers. And you can make generating functions of these. And we have kind of formulas for both, but in particular, you could look at this if you fix the length. So the Q bracket of n-fold products. But since the Q, I should really call this K1. But since the QK, remember, is just given by a generating function, the definition of QK for partition is the coefficient. And by definition, it's the coefficient of z to the k minus 1 in this Laurent series, W lambda of z. So this I could equally just say that I take the function W of z1 up to W if I make an endpoint generating function. So when I put W dot, it's the function that sends lambda to W lambda of z. So this product is a product of functions on partitions, now with values in some power series, Laurent series. And so you can call this Fn of z1 up to zn. And so you can ask, can you at least give it if you fix the length? And the answer is yes. And they gave such formulas. They were rather complicated as determinants. But one of the formulas they gave is using essentially Cramer's rule for solving linear differential equations. Some ratio of determinants you could turn into a set of equations, make a linear recursion. And so I found the theorem actually from their proof by working backwards, simplifying and simplifying. You can turn that into a very nice recursion. And there's a nice axiomatic description of the bracket that I think I'll skip unless somebody wants to see it. And then you can run the argument backwards. So from this proof, which is very short, you can run that backwards and give their closed formula. But I might at least give 1 or 2 of their special cases if I can find them in real time, which I think I can. I know what page they should be on. Well, it's a bit complicated. So, well, the first one, you would take theta prime of 0. It's the same theta that I talked about. And remember, theta of z divided by theta prime of 0 started, so theta of z over theta prime of 0 started z plus, I called it h2. It was actually e2 over 24 plus h4 z to the 5th, where the coefficients h2, h4, and so on were quasimodular forms, explicit ones with the recursion and a closed formula of that weight. So if you invert, then you'll get something that starts with 1 over z, and this is, in fact, f1 of z. So that's a very simple one. Okay, so f1 of z is just that in closed form. And f2 of z, I can also write down So you start with the same thing, theta prime of 0, divided by theta, but now of z1 plus z2. And then you take the logarithmic derivative of theta, and then the logarithmic derivative, the same one, but in z1 and in z2. Of course, it should be symmetric. And then the next one, it's a six-fold symmetry. So you symmetrize completely something more complicated, but they're complicated determinants. As I say, there is an inductive formula. So we do have kind of explicit formulas in terms of theta functions, but they become very, very complicated. It's determinants. But that also leads to, there is a very nice axiomatic characterization. But in the paper where I found this simpler proof of their theorem and these other examples, I also found one, two small, what are they called in the Greek, when you have a thing that belongs with the theorem? An extra extension, not a corollary, but a, no, after a theorem. Something that extends it. What? Scholion. That sounds very good. My Greek is not as good as some people's Greek. So the two statements that I want to add are the following, and then maybe I'll even stop for today on that. Well, it's a little early, but if I speak very slowly, I'll be able to stop with that and save myself a lot of juice. So we had this map, but it's still written here. R is the ring generated by the Q's, and the Q bracket, the theorem was that if you have, so R is graded, where Qi has degree I, so then RK is things of degree I, and the theorem said that not only is the Q bracket of anything in R a quasi-multiple form, but it preserves the grading. So if you think of my Lie algebra, which I've erased, remember the Lie algebra had three maps from M star to itself. One of them was multiplication of F by the weight. So to say that this is the same weight simply means that if I apply the weight operator to FQ, then that's the same as if I apply the corresponding weight element here, which is K times QK. So this is the weighted Euler operator. So we already have that the weight operator is somehow compatible with this Q operator. That's not quite trivial, but it's part of the Bloch-Okounkov theorem that their map preserves the weight, which I didn't actually say in my proof, but if you look at it, you'll see that everything is graded, and the proof that I gave trivially preserves the grading by induction. Okay, then the next one was D, and D, remember, was Q d by dq, which was just the derivative in tau up to a factor d by d tau. And so I wrote it on that board. I erased it, although I didn't have to. I never used that board again. D was that, and there I already gave the formula. If you apply D to a differential operator, I gave it last time, repeated it today, then, except now since I turned it upside down, I won't get the constants right unless I look. I think it was, I have a good memory, it was 37. So that's the same as you multiply F by Q2 and take the Q bracket of that, and then you take the original Q bracket and you put, and you multiply by E2 over 24. Okay? So that is 2/3 for the algebra, and then the most interesting was this D, German D, which you could think of as, I'll put it in quotations, 1/12 D by dE2. 12 times D by dE2, I think. Well, there's always a 12. I think it's that way up, yeah. You should divide E2 by 12. So then, that's how already I have to call the theorem. It took several days of fiddling with the computer to figure out what could be the right statement, and many more days to prove it. It's actually quite a mess, but there is a formula. Sorry. So if you take any Q bracket, then there is a formula for D, and it's the following formula. It's, I don't remember, I've changed the notations twice. I might as well take the ones from the paper in case anyone compares and doesn't want to get confused. It's 1/2, so there's going to be a second order differential operator, which I'll write down in 1 second. And we have a first order operator already had. Remember, D was a derivation, so homogeneous first order operator, which sent Qk to Qk minus 1. So D is simply the sum, k from 1 to infinity, Qk minus 1 d by dqk, where I remind you that Q0 is 1. So I wouldn't want to differentiate in 1, but I can multiply by 1. That's OK. So that was D, and this script D is a pure second-order operator, K and L positive, binomial coefficient, K plus L over K, Q, K plus L, D2 by DQ, K plus 1, DQ, L plus 1. And then the theorem here is it's D minus, I think, D squared of F, Q bracket. And this actually turned out to be quite useful in the work also with Müller and Chen. So we have a complete description. That's one thing I wanted to say as a supplement to the Bloch-Okounkov theorem, that one can't say how the Lie algebra acts. Now one can ask here, and somebody in fact did in an earlier lecture, can one lift this, that SL2, so we have a map from one vector space, it happens to be a ring, but the ring structure doesn't get preserved. We have a map into modular forms, which is also a ring, but it's not a ring map. And here we have an action of SL2. Can you lift it to an equivariant action? And here you see this one lifts, because the D of Q bracket is some operator. I could put the 1/2 inside, and then the Q bracket, and the weight is an operator. But here it isn't, because this is an external thing. And it turns out you can do it if you remember that E2 is the logarithmic derivative of eta. If you multiply FQ by eta inverse, so let's call that the naive bracket, it's simply the obvious thing. You just take the sum f of lambda q lambda. That's the same as the Q bracket, except I don't divide by the denominator, by what the physicists would call, as they call everything, the partition function. So if I don't do that, this one is essentially, well, maybe I then put minus the 24th to keep it clean. That's essentially eta, or 1 over eta, times the previous one. But then when I apply derivation, because it's a derivation, I get an extra term, which is adding the logarithmic derivative of eta, but that is E2, and so it just corrects for this. So it turns out, but then you have to add many more terms. It's another 2 pages of work. But just in a word, if you lift this from a map from R, but you take the naive bracket, which now goes to M star multiplied by a to the minus 1/2, so to speak, then you can lift the whole SL2 bracket, but it's a considerably more complicated formula. You have to add several terms, for instance, terms that involve Q1, that you don't even see on the level of the Q bracket, but you do see at the level of the differential operators. So there's a messy statement, but one can make this whole thing SL2 equivariant. And the other slight extension, so Zusatz, you might say in German, Skolien maybe, I thought there's another word, some extra thing that goes with the theorem, like a supplement, like the supplements to Gauss's quadratic reciprocity law. The other statement, which is much simpler, but it's fun, and I'll end with that, is, so another theorem is if F is any element in the Bloch-Okounkov ring, but I want a quasimodular form, so it might as well have even weight, so let's call the weight 2K, then if I take the Q bracket, then it's a polynomial in E2, and the coefficients in E2, E4, and E6 don't mean much, but the top coefficient, which is E2 to the K, does mean something. So there's a coefficient. So this would be actually, what I mean is you would apply this operator up to a factor of 12d, K times, and then you'll get a constant. So that's this leading coefficient, which plays a role in the asymptotics and also in many stories. And that when there is a closed formula, and it's quite, let me leave a little more space. So the coefficient of the unique top term, so this is a modular form of weight, quasimodular weight 2K, that consists of E2 to the K, which is maximum depth K, and the rest is depth less than K. So we want that top coefficient, and it's the product of two numbers. One of the two numbers depends only on the weight, and it's minus 2K minus 3 double factorial divided by minus 12 to the K. So that's the number that only depends on the weight. And here I should remind you, well, 5 double factorial, I think everyone knows. It's 5 times 3 times 1. But by backwards deduction, you find that minus 1 double factorial is 1, and minus 3 double factorial is minus 1. So if K is 0 or 1, that's what I mean there. And then there's a constant that does depend on F, but mu, which is a map from R star to Q, now it's a ring homomorphism. And so I only have to say what QK does, and QK goes to 1 minus K over K factorial. So that's which makes sense because Q0 is 1, it has to go to 1, but this is 1, and Q1 is 0. It has to go to 0, but this is 0. And all the others can go where they please since they're free generators. And this is what they please. So that's a nice closed form. It's also, it takes like a page to prove this. So these extra things are, this one is very tricky, that one's less tricky. But these are slight extensions of the theorem to tell you exactly how this map looks. So I think that's a good place to stop for today, and therefore for this week. We have one more week left, next Tuesday and Thursday, and then I'll tell something about this evaluation map that I mentioned, from quasi-modular forms to polynomials, which is quite fun for many other applications. And then if you know a modular form here, and you know the polynomial here, it gives you information about the growth of the coefficients, so the average growth. And that's what you need for the application to the volumes of and the Siegel-Veech constants, as Martin explained in his lecture last week. So the applications to that will involve things about growth and also this wonderful thing with the TP that I haven't yet gotten to, that I told. And there's one last fun thing which has nothing to do with anything at all. We have an appendix to our paper of, I think, 7 pages, which is working with very strongly divergent power series. So I'll just say that to whet your appetite. Usually, when you go to school, meaning university, you learn about power series, and the only good ones are the ones that converge. The rest are, ugh. People used to not even believe they existed, and then they discovered the word formal, but they're just some, it's like complex numbers, irrational numbers. You feel queasy. So if you look at a series like sum x to the n over n factorial, every mathematician is happy to convert it to every x. If you look at a sum like 2 to the n x to the n, mathematicians are a little less happy. It only converts if x is less than a half. If you look at n factorial, x to the n, everybody's unhappy. It always diverges. We are also unhappy because it's not divergent enough. This is rapidly divergent, but we study things that are very rapidly divergent, which means it's strictly worse than n factorial. N factorial to at least alpha, where alpha is strictly bigger than 1, typically 2. And then it turns out that lots and lots of processes on infinite series work wonderfully in this class and don't work in any of the previous classes. They're actually better. And this was a real surprise. So for instance, if I give you a power series starting with x, with rational coefficients, and you know the first 100 coefficients, and you know the asymptotics. And now I tell you, this series starts with x, and it's an inverse power series. What are the asymptotics of that? You don't have a clue. There's no way from the first 100 coefficients and the asymptotics of the nth coefficient to high order to deduce. But if it's very rapidly divergent, then you do know. If it's very rapidly divergent, all things like composition and inversion of series are compatible. So I'll make a little digression on that because that was a fun side thing that we couldn't find in the literature. We had to prove these things ourselves to get the actual applications to Esconsor's conjecture and things like that. You need the growth, and these are all very rapidly divergent series. And first we thought that would be our undoing, but it turned out to be the only reason it worked at all. So that was kind of a fun surprise. Okay, so see you, some of you, next week.